Now we'll discuss application of heat conduction with a nuclear heat source. As we know, heat conduction with a nuclear heat source is a fundamental process in which heat is generated by nuclear reactors or radioactive decay is transferred through materials. This thermal energy is crucial for numerous applications in power generation, space technology, then defense, healthcare, and more. We can see below is the comprehensive and detailed explanations of various applications. And also we have assumed two predictive models to enhance our study on this topic. The first one is nuclear power plants. In commercial nuclear reactors, nuclear fission generates an immense amount of heat within uranium or plutonium fuel rods. This heat is conducted through the fuel material to the metal cladding and into a coolant, usually water or gas. Effective heat conduction ensures thermal regulation, prevents overheating, and supports efficient conversion of thermal energy to mechanical and then electrical energy. Advanced reactor designs incorporate materials with higher thermal conductivity for improved efficiency and safety. We can see uh, the advantages of nuclear power plants in this discussion. Now I will move to radioscope thermoelectric generators (RTGs) in short form, and it is used widely in space missions. We can see this application, it is on space level too. So we will discuss RTGs. RTGs utilize the decay heat of radioisotopes such as plutonium-238 to generate electricity through immense amount of thermoelectric modules. This heat is this heat must be conducted from a decaying material to thermocouples efficiently, often in the vacuum of space where convection is not possible. RTGs power long duration missions like Cassini and Mars rovers, providing consistent power regardless of solar availability. Now I will discuss about nuclear submarine and naval propulsion. Naval reactors produce heat through fission and conduct it through core components into steam generators. This steam drives turbines for propulsion and electricity. Heat conduction efficiently directly affects reactor compactness, silent operation, and stealth capabilities. Effective thermal management is essential for sustained underwater operations. We can see the applications of heat conduction with a nuclear heat source in nuclear power plant at space level, and now we are seeing at the navy level, the underground submarine level. Now I will discuss about small modular reactors. Its short form is SMRs. SMRs are designed for passive safety and minimal human intervention. Heat generated during operation is conducted away using natural convection and conduction. The design leverages gravity and thermophysical properties of material to avoid active cooling systems, enhancing safety, simplicity, and cost effectiveness for deployment in remote and in urban areas. Medical isotope generators, which is our fifth application. These systems use short-lived isotopes like technetium-99m, which emit heat during decay. Conduction through the shielding materials is necessary to manage this decay, heat, and maintain operational safety. Efficient thermal design ensures precise isotope generation for diagnostic imaging and radiotherapy without overheating sensitive components. So it is used in medical isotope generators too, the application of heat conduction with a nuclear reactor. Now I will go to space nuclear propulsion. It is basically for future use. Again, space terminology comes here in the picture. Space nuclear thermal propulsion system envisions reactors heating hydrogen gas via conduction. This heat transfer enables the gas to expand and produce High thrust for thermal travel. Due to thermal travel, the system relies on materials that can withstand extremely high temperatures and provide stable thermal gradients, enabling rapid travel such as Mars missions. Now we will look at some wastewater management. Basically, we will look at the nuclear waste management. Spent fuel emits decay heat long after removal from reactors. Conduction through engineered barriers in dry cask or geological repositories ensures the heat dissipates over the time without increasing storage temperature. Predictive thermal models are used to design long-term contaminant systems that prevent leakage, preserve structural integrity, and ensure environmental safety. So we can see here environmental safety is the main cursor of nuclear waste management, as this can cause various damage to our environment. So its safety is one of the most important aspect we need to take into consideration. And it is also used in defense and military reactors. Deployed in mobile and tactical environments, these reactors require compact, reliable heat conduction systems to dissipate energy without noise or complexity. Passive conduction based cooling systems reduce moving parts, enhancing durability and stealth. These systems support prolonged off-grid operations by providing electricity and heat in the grid. So we can see that defense and military reactors uses all nuclear heat source uh, for its campaign uh, for its campaign and for its various purposes as mentioned here, like without noise or without complexity we can choose nuclear reactors. Now I will talk about some advanced research reactors, which is used in research in material science, neutron imaging, and isotope production. These reactors generate intense localized heat, sophisticated heat conduction pathways using high thermal conductivity materials like beryllium, graphite ensure accurate thermal gradients, enhancing experimental outcomes and reactor control. This is the application of in advanced research reactors. Molten salt reactor, this short form is MSRs. In MSRs, fuel is dissolved in a molten salt mixture, which acts as both coolant and fuel medium. Heat conduction through the reactor vessel and secondary heat exchangers play a vital role in maintaining reactor stability and transferring heat energy for heat energy generation. These reactors operate at high temperature and with low pressure, requiring advanced conductive materials. Now I will talk about fusion reactors. Example ITER. Although still it is under development, but we will discuss a few outline about it. Fusion reactors like ITER involve plasma confined in magnetic fields, generating intense heat on reactor walls. Heat conduction is used to remove this energy safely. The thermal design must have managed neutron bombardment and intense heat fluxes using specialized material like tungsten and beryllium in layered heat shields. So we have discussed fusion reactors, which is basically under development, but it will come into picture within few years. Now we'll discuss nuclear powered industrial heating. In remote or energy-intensive industrial settings, nuclear heat source can provide direct process heat. Conduction through reactor components to the target process ensures precise control of industrial heating for applications like hydrogen production, synthetic fuel synthesis, and desalination. So we can see in remote or energy industrial areas, it is very useful. Now I will discuss autonomous underwater vehicles, AUVs, and deep sea probes. Experimental nuclear powered AUVs uses decay mechanism and in which heat conducted through thermoelectric materials provide electricity and propulsion. Such systems are being explored for deep sea research where sunlight and battery charging are impractical. So we can see applications of heat conduction with the nuclear source fuel source is in deep sea level, in high altitude, in on natural earth level. We can see it's used everywhere. Now it can also be used in nuclear batteries, photovoltaics. These are compact sources that generate electric from beta decay. Heat conduction plays a key role in thermal regulation, especially in sensitive electromagnetic environments, ensuring longevity and stable performance of low pressure system in satellites, implants and sensors. So we can see here the applications in nuclear battery sources. Now we have just predicted few models for heat conduction in nuclear system. First is finite element thermal modeling, which is short form as FEM. In this model, we have just predicted a reactor which divides the component or storage system into small elements and solve the heat conduction equation numerically. It helps in predicting transient and steady state thermal behavior under various boundary and initial conditions. Widely used in reactor design, safety analysis, and heat shield optimization. Second is Monte Carlo heat transfer model. This static model is used to stimulate random heat paths within complex materials. It's beneficial for heterogeneous media like composite fuel rods or for shielding materials. By averaging over many simulations, it predicts effective thermal conductivity and heat dissipation characteristics accurately, aiding in robust design. So we have discussed all the applications of heat conduction with a nuclear heat source, and we have predicted two models at last, which includes FEM, finite element thermal modeling, and Monte Carlo transfer model analysis, where we can see its application in space, we can see its application on Earth level and also in deep sea level.
So, at last, to conclude our study on heat conduction through a nuclear heat source, let's bring together all the key points we have explored and understand their importance in both theory and practical applications. We have started with the concept of a nuclear fuel element, which can either be cylindrical or spherical in shape, and these fuel elements are typically made up of fissionable materials that generates heat internally through nuclear fusion reactions. And this method is quite different from most heat conduction problems, as in earlier cases, heat is applied at the boundary. But in our case, heat is generated volumetrically, that is, throughout the material itself due to collision and reaction of fusion fragments with the fuel atoms. Heat is generated continuously. And next, we have focused an important aspect that this heat generation is not uniform. It is actually maximum at the center of the fuel rod and it decreases as we move towards outer edges in radial direction. And this variation was modeled using a parabolic distribution function mathematically, which can be written as Sn equals to Sn naught into 1 plus b small r square divided by capital R square, where Sn is the local heat generation rate at any radial position r. Sn naught and r and b are non-constants, where b is a positive constant which controls the position of the parabola, and small r is radial coordinate, and capital R is radius of the fuel element. Next, to analyze how a heat conduction through the material takes place, we have applied shell energy balance approach. This method allows us to take a very thin cylindrical or spherical shell element and apply the principle of conservation of energy, where we have seen in question number 1 and question number 2 also that many terms drop out to be zero, and there are reasons of becoming that term zero. Like in both the questions, question number 1 and question number 2, there is no convention inside the solid. So all the convention terms we have neglected, and also there is no mechanical work being done. So all the mechanical work terms or work terms has been neglected. So at last we have simplified our shell energy balance equation, which consists of mainly two contributors. One is conduction in and out of the shell, and second one is internal heat generation within the cell. And this simplification gave us a differential equation, which we then solved using integration techniques and appropriate boundary condition. And whenever there is a need of logical boundary condition, we have applied that also. By using different boundary conditions, we can get the values of constant, and then we have put that value of constant in the temperature equation. So we have got temperature distribution across the fuel and cladding, and most important, the maximum temperature. Since this maximum temperature is very much critical because it indicates the thermal limits of the reactor. If center of the fuel gets too hot, the metal could melt or suffer damage, potentially leading to a failure of the fuel elements. That's why engineers need to design the system carefully by choosing the right fuel radius, cladding thickness, thermal conductivities, and coolant conditions to make sure that the temperature stays within safe limits. Another insights we gained is that thermal conductivities of both the fuel and the cladding plays a huge role in how the temperature is distributed. If the fuel has a low thermal conductivity, the temperature gradient inside it will be very steep, meaning the center will be much hotter than the edges. This reinforces the importance of material selection and geometry optimization in nuclear fuel design, and also the heat transfer coefficient at the coolant interface, which we have denoted by HL. It controls how effectively the cladding can transfer heat to the surrounding. A high heat transfer coefficient ensures effective cooling, reducing the outer temperature and indirectly helping reduce the central temperature too. Uh, we have seen how heat conduction through a nuclear heat source is governed by the balance between internal generation, material properties, and boundary heat transfer. This process of modeling the system through energy balance and solving the temperature distribution gives us a powerful tool to predict, design, and optimize the thermal behavior of nuclear reactors. Understanding this concept is not only important, but it is also vital for real world nuclear safety and performance. Engineers and reactor designers rely on these principles to build systems that are efficient, safe, and reliable over long operation lifespans. So, through this case, we have moved from a theoretical energy balance to a deep understanding of how nuclear fuel behaves under internal heat generation and how to manage that heat safely.